Alright, we might actually get done. This might be the last video. If not, there'll be maybe a short one after this. But I think we'll get very close to done. So again, we've established I need, at 37 degrees C, I need to know the specific volume. Well, we don't know what this curve looks like. All I know is I've got these data points. Alright? I've got 30, and I've got a specific volume value, and I've got 40 and a specific volume value, and I need to know at 37, somewhere in between those. Okay? So it could be, the curve could look like this in between them. It probably doesn't. It's probably just a nice little soft, straight curve. But, you know, there was a famous guy, I believe his name's Euler, that says over a small enough region, all functions can be approximated as linear. And in fact, there's the Euler method as a way we solve differential equations, where we assume over a very small region, we assume a linear approximation. So how do we write the equation for this line? Well, you could try to write a y is equal to mx plus b type of equation, but there's another form of linear equation that's much better suited for this, that says y minus y, the y value at some point A, divided by the y value at some point B minus the y value at point A, is equal to x minus the x value at some point A, divided by x value at point B minus x value at point A. Well, I don't have y and x, so we just give up and we say this doesn't work, right? No, it doesn't matter what y and x are. In this case, I've got temperature and volume, but it could be, in an x problem, it's going to be temperature and internal energy. It could be pressure and internal energy. It doesn't matter. Y can be anything, x can be anything. That's what algebra should teach us, right? We just got to go find what we don't know. Well, what do we not know? I don't know V37. I can look up V30 and V40. I know these, right? So if I say, well, at 37, I know I've got the values for 30 and 40. I'm looking for 37. I'm looking for V at 37. Well, I can minus the V value, the known V value at 30 degrees, and divide that by V value at 40 degrees and the V value at 30 degrees. And that will give me, the only unknown here is the one that I can't look up because it's not in the tables. Okay? So, if I solve that, V37 is going to equal, this is 7, this fraction right here is 7/10, right? This is 7 divided by 10, multiplied by, and the difference between the 30 and 40 values here, right? So the 40 value is 0.0465456. Now look these up on your own. Make sure you understand how I'm getting these. You're going to have to get really good at this. The V value at 30. Right? So again, I'm taking this fraction, multiplying here. Okay. So V at 30, 0.042115. 0.042115. Okay. Those are both, this is metric, so those are both going to be meters cubed per kilogram. Move this up so you can see a little more of it there. Okay, and then add to it, and so we're going to add this over here also. So again, I'm solving for V37 here, okay? So I'm going to add this to this quantity here, the V at 30, which is this value here, 0.042115 meters cubed per kilogram. Okay. Here's my time. Okay. So I'm going to take this difference, 0.046546 minus 0.042115. That difference multiplied by 0.7, 7 divided by 10, add to that 0.042115. Now here's the first check. Do you get a value between these two? Because your value should be between these two, right? Again, remember, I'm trying to find some point here in between these 2 points. So I need to be between these two. Well, I am between these two. Can you tell if I should be closer to one or the other? Yeah, I should be closer to the 40 value than I am to this one. So this looks actually okay. V is equal to 0.0452167. And that's too many significant figures, honestly. All right, but that's okay. We'll leave it for right now, because this isn't going to be a final answer in a normal problem. But that's how I would interpolate between these 2 points. Now, I'm about to lose my voice. I've got one more thing to talk about. So I'm going to leave. The original problem asked us to find both the U and the V values. And you can find the U values on your own. I'm going to let you find the U values on your own. Just go look up. You're looking for U37. Go look up U at 30. And U at 40. And go solve for U37 and do it on your own. And it's good practice. Okay? Send me the value and I'll tell you whether you're right or not. Email it to me and we'll see how close we are. Okay? All right. So I've got space in there we can talk about interpolation. All right. So last, very, very last thing. What do you do if you've got a compressed liquid? Okay. What do you do if you've got a compressed liquid? How do we know if we've got a compressed liquid? Well, I've been talking about that here. Right? If I've got, if I find myself on this side of the PT curve, or if I find myself to the left of the dome region, I've got a compressed liquid. Now here's the thing. Once I've established I've got a compressed liquid, if I know the temperature, that's my driving force. The temperature is the only real thing that matters if I have it. Now if I don't have the temperature, I have to use the pressure and go from there. But if I know the temperature, that becomes the important issue. If we think about the volume or the density, right? If I've got a liquid, it doesn't compress. I can apply as much force to it, as much pressure as I like. It doesn't really squeeze. It doesn't change volume too much. It will a little bit. But if I heat it up or I cool it down, that will change the density or the volume quite a bit, as opposed to applying pressure. Right? So for the most part, pressure really doesn't impact U, V, H, or S. Right? And what it's saying here. Debating what I want to write. Let's just write this out on paper. I can scribble that. It's not displaying very well there. Let's just write this out on paper. Okay. So 4 compressed liquids. Let's just write this way. For compressed liquids, your specific volume is going to be very, very close to the specific volume of saturated liquid at the given temperature. So if you have a temperature, just go look up the specific volume of saturated liquid at the given temperature, and that will give you a very close approximation. Same thing for the U value. Same thing for the H value. Same thing for the S value. Go look up at the given temperature the value for saturated liquid, and that'll make a really good approximation. When you see this in the text, you'll see they say, well, let's just use Y to represent U, V, H, or S, and this is an F, although it's not displaying well on my tablet. Use the saturated liquid value, and that gives you a really close approximation there. Okay, and that's what I'm saying here. There's 2 different ways of writing the same thing. Now, if you go on there in the text and look at this, they will say that for the H value, there's a little better approximation because by definition of the enthalpy, the pressure can have a bigger impact. But here's the thing. Unless this difference is huge, because the specific volume of a liquid is going to be very, very small. So unless this is huge, you're multiplying this difference, the difference between the current pressure and the saturated pressure, you're multiplying this by a very, very small specific volume value, because for liquids, density is going to be very large, and the inverse, the specific volume, is going to be very small. So unless I'm multiplying a very, very large quantity to this is going to be very, very small, and I'm going to add a very, very small quantity to this, which is probably not tiny. So what I'm saying is this probably will not affect this value by much. This is probably going to be like adding a couple of pennies to a $100 bill. How much is it really going to matter? It probably doesn't matter too much. So unless this pressure difference is huge, this is probably just fine. Okay. If you do have a compressed liquid table for liquid water, it doesn't start until you get into the really high pressures, several megapascals, so multiple atmospheres. There's only just a couple of times where we actually use that table. Most of the time, this works just fine. If you know the temperature, just go look up the specific volume or look up the property for saturated liquid at the given temperature. This is the only thing you can do for R134 is you don't have a compressed liquid table for R134, so you have to do this for that substance. For water, this normally works just fine for our purposes. Okay. We won't deal with compressed liquid water very often, but when we do, this is a nice little tool to give us these properties. Okay, so last thing, one more time, how do we do this? Well, know what your substance is, know what properties you're given, right? And it's kind of similar. We talked about problem solving last time. What are you looking for? What's known? What's the fundamental thing at play? So which table am I actually going to use? And then how do I use that table for my specific scenario? And then go solve. What else do I need? All right, guys, I hope that's a lot. It's a lot to try to get done in one lecture. It's a tough lecture in the summer to get done. I hope these videos are helpful. I've tried to do as close as I can to what I normally do in lecture in the hopes that that's helpful for you. If you have suggestions, you have ideas, if something's not clear, please let me know. That's the disadvantage of this online format is I don't know what's getting through and what isn't. But you know, me explaining it's one thing. You actually putting it to practice and problems is another. So, you know, but again, if something's not clear, email me, or if you got a problem that you just aren't sure on, shoot me an email, and I will get back to you, and send me a picture of your work, and I'll respond back with some suggestions. We'll go from there. All right, guys, keep doing what you're doing, and I will see you and talk to you, or you'll see more of me, or whatever the case may be. All right, guys, have a good one.